In this video, we're going to take a quick look at seeing how two-variable analysis works in Google Sheets. So I've already started by putting in some information here. I'm doing a test correlation between two unit tests from my advanced functions class. This is real data from last semester. So here I have in the marks that they got on their trig test, which for us was unit 4. And as well, they had marks for their trig functions test, which was unit 5. So these are all the student marks there. Obviously, I didn't include the names with them for good reasons, but this is how the student marks compared. And we see, oh, the student went down quite a bit. The student went down a little wee bit. The student went down a bit. The student went up 5%, and so on. So obviously, there is no exact mathematical pattern that will predict what the second test was relative to the first, but is there a statistical pattern if we look at the long range, if we look at the class as a whole? So what I'm going to do really quickly is I'm actually going to just put this down to 100% so you can see all the data on the screen, and I realize it's a little bit small, but I'm going to highlight it. And I'll also point out, actually, as I'm highlighting it, actually before I highlight it, that there is one value missing. And this was a student who did write test 4, but did not write test 5. And I needed to record marks for a mark update, and I didn't want to leave a 0 there because the student was performing quite well, so I didn't believe that that was a valid thing to include, but I did get them to actually write the test later. So what I'm going to do is see if I can predict what their mark would be on the second test and then compare that to what they actually got on the second test. And again, I'm going to keep pointing this out. Just because we have a pattern overall doesn't mean it follows for every person. This person went up 5%, this person went down 3, this person went down 7, this person went down quite a bit, this person went up 2. So for each individual person, we're not sure it'll work, but it's really the best we can do if we're trying to make an overall prediction. So I'll take all of this data, and now that I've highlighted, I'll go back to 150% just so you can see it a little bit clearer. And I'm going to go up and click on Insert. And one of the options here will be a chart. Now, by default, scatter plot is usually what Google Sheets and any other spreadsheet will do with two data sets like that. There are other types. You could change the chart type. There, I can say words. Chart type up there if you'd like to. There's a whole bunch of different options. However, the one we want was the default, the scatter plot, so we'll leave it as that. I'm just going to slide this up here so we can see it a little bit better. And now the first thing I want to do is basically look at that graph and see, does it look like there's a correlation? I see what looks like a pattern. It seems to be going up as we move to the right-hand side, which is really just a way of saying students with higher marks on test 4 tended to do better on test 5, and students with low marks on test 4 tended to get lower on test 5, which actually probably makes a lot of sense. Okay, is that a strong, weak, moderate correlation? It's really hard to eyeball this. I'd say it's moderate to strong, perhaps, but let's let Excel do the exact values and figure out what it is. So actually, before I do any of the analysis, I'm going to change the scale of my axes a little bit to better show the data. This is a personal preference, but I know a lot of people feel the same. I hate when data is like basically off the edge of the chart, or is, in this case, there's nothing that's off the chart, but there's a few that are like on the edge, and I don't care for that. So first of all, I'm going to actually adjust my y-axis. So I'm just going to click on y-axis. All I did was left click on it once. And if I look over here, I have a whole bunch of things for my vertical axis that I can change. And it looks like the smallest value is in the high 40s, and it goes up to 100. So I think I'm actually going to go to, let's say 45 to 105 and see what that looks like. Okay, now the one thing I don't like about this necessarily is that it's jumping by 20s, which is okay, except it's jumping by 20s and they're not each multiple of 20. If it was going up by 20s, I'd like it to be like 40, 60, 80, 100. I don't really like these fives that are in there, so maybe I'll just change this one to from 40 to 110, just to get rid of that problem. Okay, there we go. Now we're going up by 10s, and each of those is a multiple of 10. So that fits all my data on vertically. Now I'm going to do the same thing horizontally. Now it looks like my smallest data point, actually if I click on it, I think it will tell me what the data point is. or I'm mistaken. But it looks like it's probably around 60 something, so or like low 60s. So what I'm going to do is click on the bar, change the minimum value to 60, and if I'm wrong, I can always fix it later. And the maximum, I'm going to do 110, just again to try and fit things on. Okay, and now I think that graph looks a little wee bit better. It doesn't start at 0, 0, but that's okay. Graphs don't have to. I think it better shows the picture of what the dots look like. Now that I've done that, I'm going to click on the actual data itself. And if I go over here on the right-hand side, I can do a whole bunch of things. And what I'm going to do is actually add a trend line right there. So by default, it's going to give me a linear regression, which basically just means a line of best fit. And if I choose to do different types of regression, I can just drop this down and choose one of these other types of functions. Maybe exponential or polynomial is better. I don't think logarithm will work. Power series and moving averages, honestly, don't use those. They're kind of weird. But linear, exponential, polynomial all sound like they're plausible, but we'll leave it on linear for now. So if you do use Excel, normally there would be a button down here to show equation as well as showing R² value. We don't have that option in Google Sheets, but the good news is under label, if I click use equation, it will show me what the equation is. Okay, so this is telling me their mark on the second test. I should take the first test mark, multiply it by 1.25, and then subtract 27.7. I realize this is kind of a weird format to write it as in plus minus 27.7, but it's really just saying multiply it by 1.25, subtract 27.7. So that's the relationship between the two variables. I'm going to actually add the R² value on there to see if this is a good correlation or not. And R² is 0.653. Now 0.653, if you're thinking back to our correlation values, we said that a strong correlation was 0.67 or bigger, and a moderate correlation was between 0.33 and 0.67. So a bunch of people are going to jump to the conclusion that this is a moderate but closing in on a strong. But keep in mind that those numbers that we're using were actually for R, not R². So from my R² value, 0.653, I'm going to take the square root of it and find out that R is actually 0.808. So 808 is actually a relatively strong correlation. So what that's telling me is that my data is fairly strongly correlated, which means there's a good chance that my regression will work. So that means my prediction that the equation is going to give me actually is probably a fairly reasonable prediction. May not be perfect. There's always points that are above or below. Obviously, we're looking at this graph, not every point falls on the line, so we can't say that we can guess exactly given one value what the other value will be, but we can get something reasonable. Okay, just before we go any further, I do want to see what the difference will be in this R² value if I change to different types of regression. We are going to come back and work with the linear, but let's see if one of the others is any better. So linear is 0.653. I'll change it to exponential. Actually, it gives exactly 0.653. I will be honest, that's actually kind of a coincidence. The odds of those being the same is pretty low. And polynomial, 0.655. Okay, so that's actually just slightly better than a linear regression, but it does create a more complicated equation. Now, for those of you who are having trouble reading what that equation actually means, usually we would write a polynomial equation as, ax² plus bx plus c, and this is writing it backwards. It's putting the constant first. And this last part here, and this is actually, I think, kind of important. It's saying the coefficient of the x² is 6.49 to the times 10 to the exponent -3. So really that's the same thing as saying the coefficient of x² is 0.00649. 0.00649. That means there's almost no coefficient to the x² value, which means the x² value is not a major part of the contribution. So Yeah, let's just go back to linear. Linear is a lot easier and it gives us a r squared value that is, again, pretty much as good as any other kind we're going to get. So now that we've done that, we've basically done everything we need to do on the graph. We found an equation here. Let's take this one person who's missing, and we can't type in the value that they got on test 5 because we don't have it, but I can type in that their test value is probably approximately equal to 1.25 times their first test value minus 27.7. And so if I use that as a prediction, it predicts that their mark on this on test 5 is going to be 83.55%. And I will tell you that I actually have the real mark that that student got, which was 84%. So our prediction in this case turned out to be really good. There's never a guarantee, but I can say I actually have used this method several times in the past for students who have missed a test, especially if it's like right before midterm, where I know they're going to make it up. I know they're going to write it eventually, but I have to have something to enter in for their midterm mark that I believe is reasonable. So I've made this prediction before, and it's often within a couple of percent of the correct answer once they've actually written the test. So it's a pretty good indicator. It's not perfect, but it is a good indicator. Okay, so that's pretty much it. That's how to do two variable analysis. We've basically found our regression, we found our coefficient of determination, and then from it our coefficient of correlation. I guess I should point out when we found our coefficient of correlation, we took the square root of r squared, which could either be the r could be either positive or negative. We can't tell that from the equation r squared equals 0.653, but we could just look at the graph and say, well, in this case, correlation is obviously positive. As one value gets bigger, so does the other. So our r value is going to be a positive number. If this had been sloping downwards, which in this case would be a really sad thing to happen, the better you did on the first test, the worse you do on the second. But if that was the case, um, the downward slope would tell us that it's a negative regression and our r would have been a negative value. So mathematically, we can't tell if r is positive or negative, but looking at the graph, we do. That brings me around to my very last point, which is why does it give us r squared instead of r if usually the r is what we want, the correlation? One of the major reasons would be that for a linear regression, figuring out r is pretty simple. Whether it's positive or negative makes a lot of sense. But for something like a quadratic regression, where it's a parabola, we have a parabolic shape in the data, it doesn't make sense to give an r that's positive or negative because for a while it will be negative and for a while it will be positive. And that will always be true for a parabola. So giving an r value is kind of irrelevant with nonlinear data, but an r squared value gives the same information. So I'm going to stop there. And if you've got questions about how correlation works or how to do two variable analysis with Google Sheets, let me know.